Okay, just quickly before we talk about enzymes today, I'm just going to go over and review what a chemical reaction is specifically. A chemical reaction is defined as when substances are making new chemical bonds or breaking old bonds. The reactants are on the left side of the equation and the products are on the right side, on the left side of the arrow, and products are on the right side of the arrow. So in the reaction Na plus Cl, they are the reactants, and then it forms NaCl, that's the product. This is called an oxidation reduction reaction. Sometimes people abbreviate that as a redox reaction. A redox reaction occurs when one atom loses an electron, that's called oxidation, and when one gains an electron, that's called reduction. So you see that purple arrow in the diagram moving one electron to the other. That's an example of an oxidation reduction reaction or a redox reaction. Enzymes are specifically for speeding up these kinds of reactions. And so we're going to talk more about enzymes. So what are enzymes? Well, enzymes are defined as organic catalysts. Anything that is organic is something that was once living or is living. But what exactly is a catalyst? A catalyst is defined as anything that speeds chemical reactions without being changed itself. Now, catalysts are not necessarily organic. They don't necessarily come from living things. In the liver lab, we used manganese dioxide. It was a black powder and it caused the hydrogen peroxide to bubble. That's an example of just a plain old catalyst. It's not organic. It's something that's found in the earth. An enzyme is a specific kind of catalyst that's produced by cells and it speeds reactions in the body. So therefore it is considered organic. Enzymes and catalysts, but enzymes increase the rates of reactions by at least 1 million times. Okay, so how exactly do enzymes work? How do they speed reactions up by 1 million times? Well, they lower something called the activation energy. They cause the reaction to require less energy. It's the amount of energy needed for a reaction to occur. So if you look at this graph, and a lot of students have trouble with this graph, look at the red line first. As you're moving from the left to the right, in order for a particular reaction to occur, energy has to be added into that reaction for it to occur. So you see the red line going up, and that's called the activation energy. Once it hits a certain amount of energy, then the reaction can occur, and the amount of energy decreases rapidly. The green line is the amount of energy that's required, the activation energy that's required when an enzyme is present. Notice that the green line doesn't go nearly as high as the red line, so not as much energy needs to be added. Let me give you an example. Hydrogen peroxide is a perfect example. If I leave hydrogen peroxide on a shelf for 10 years, all of the bubbles will eventually come out of the hydrogen peroxide, but that takes an enormous amount of time. It's very slow, and the energy is slowly adding up. I could get all the bubbles to come out of hydrogen peroxide if I added an enormous amount of energy to it by boiling it. Or I could get the bubbles to come out of hydrogen peroxide by shaking it violently. That's the red line on this graph. All those examples are red lines on this graph. Me adding a lot of energy, either through heat, either through shaking it, or just letting it sit on a shelf and absorbing energy for year after year after year. That's that red line. It takes a lot of energy for the hydrogen peroxide to bubble completely. But the moment, if you remember, the moment that we dropped in manganese dioxide, it bubbled instantly and no energy had to be added to the solution, or almost no energy. So that's where that green line comes in. The same thing happened when we added liver to the hydrogen peroxide. It had enzymes in it and it caused the hydrogen peroxide to bubble quickly without us having to shake it, without us having to heat it, without us having to wait for years and years. So it speeds it quickly by lowering the amount of energy needed for that reaction to occur. Okay, so how do they do that? How do they make these reactions occur? Okay, so how exactly are these enzymes speeding up these reactions? Well, scientists have what's a model that's called the induced fit model, and this is what it says. It says that enzymes have shapes, kind of like puzzle pieces, but these puzzle pieces can bend slightly to fit with whatever molecules they're supposed to react with. Those molecules are called substrates. When they fit together like puzzle pieces, the chemical bonds then in the substrates either break or form, whatever. That's a chemical reaction. And so that's what the enzyme is doing, is fitting with them and causing bonds to break or form, and it causes it to happen a lot faster. Take a look at the diagram down at the bottom. The big gray blob is your enzyme. In the liver, the enzyme was called catalase. And then the green is the substrate, the molecule that we're trying to have that chemical reaction occur to. So maybe this would be hydrogen peroxide, for example. So you see the two of them fit together in the second diagram, and then the enzyme causes bonds to break or to form. In the case of hydrogen peroxide, bonds are being broken and rearranged, so that what you end up with hydrogen peroxide is two different products. You end up with water and oxygen, sort of that teal colored shape and the orange triangle. And the enzyme, notice, is unchanged. It's able to now work on another hydrogen peroxide molecule and break it up, and so forth and so on, 1,000,000 times a second. Now, we learned in the liver lab that enzymes are affected by certain environmental conditions. The first factor that affects enzyme activity is the temperature. Enzymes work best at a particular temperature, usually body temperature. In the graph to the right, temperature in Celsius, 36 degrees is body temperature, 98.6 Fahrenheit. And notice that that's the peak of the enzyme. The enzyme works best there. Once the temperature starts going up, it suddenly drops off and is completely ineffective. That high body temperature in that circumstance is what happens when someone gets a fever over 108 degrees. Enzymes are made of proteins. Proteins denature, which is a fancy way of saying they melt at 108 degrees. So when someone has a fever over 108 degrees, the proteins and enzymes in their bodies begin to denature and they can't function correctly, so all the reactions begin to slow down. And a fever that high is deadly. In the reverse, when a person's body temperature gets colder, that's called hypothermia, when their body temperature starts to drop below 98.6 or below 36 degrees Celsius. The enzymes don't denature anymore. The enzymes simply slow down, and all the reactions in the person's body slow way down. This is one of the reasons that children who fall in an icy lake and drown are sometimes able to be revived even 20 minutes after the fact. It's because their biological processes slowed down so much because of the cold temperatures that once they're warmed up again, those processes are still able to function correctly. So most enzymes function best within a critical temperature range. Another factor that we discovered in the lab that affects enzymes is the pH. Catalase is a pH that survives in the blood, and the pH of the blood is right about 7, so neutral. So most enzymes that are found in the blood, look at the graph, do best. They hit their peak. They're the fastest when the pH is 7. Now, if you remember, we said, just as an example, when carbon dioxide is produced in the blood, it combines, when carbon dioxide is produced by the mitochondria, it combines with the water in blood and makes an acid, and that acid causes the pH level of the blood to drop. Now, if that were allowed to continue, notice what would happen as look at the blue hill. As the pH dropped, you would notice that the effectiveness of our catalase enzyme would get worse and worse. So we are forced to exhale that carbon dioxide to get rid of that acid so that our pH stays at 7. Now, there are a couple of exceptions to that. You do have enzymes in your stomach, and they do best in an acidic environment because, of course, the stomach has hydrochloric acid in it. So notice the light green pepsin enzyme does best at a low pH, and vice versa. Your intestines actually have a basic pH. They have a high pH. So an enzyme that's found in your intestines called trypsin has its peak at a higher pH. But no matter what, they have a specific pH that they work well at, and if you change that pH, the enzymes don't function well. All right, that's it on enzymes.